Alright, so we're going to take a look at the second part of section 7.2. This is going to be a little different than part 1. If you don't remember part 1, that's fine. But on this part, what we're going to try to do is take something that has trig in it and get rid of all the trig. Right? So we're going to take something with sines and cosines or inverse trig and get rid of it so it's just algebra. Like squaring, square root, add, subtract. And what this is going to do is basically make it easier to work with the function so there's no trig. Okay, just algebra. And it's usually going to involve Pythagorean Theorem, which means you're going to have like things squared or square rooted in the final version, and fractions. Okay, there's usually a fraction as well. So what we're going to have, just to show you, is you're going to have a problem like this. Okay? The sine of the inverse cosine. And what I want is a formula for that doesn't have any trig in it. Like x squared plus x divided by 2. Something. Some algebra formula that would be equivalent to this with no trig in it at all. Right? So the key is to start with the inner trig function. Right? So in the problem we're going to look at, it would be inverse cosine. So you start with the inner trig function. And at least for me, what it kind of helps to do is make a diagram. Once you get used to it, you might not need the diagram, but at first I think it'll make sense. So the kind of diagram we're going to draw is a right triangle diagram. Okay, so the ideas of opposite, adjacent, and hypotenuse are going to come up here as well. Now, if the inner function contains inverse trig, which the first one we're going to do does, it helps to rewrite that in terms of regular trig. And that's very easy to do. We'll look at that. So a couple things to keep in mind as we do it. Pythagorean Theorem is going to come up pretty much every problem, especially where you have an inverse trig function on the inside. And remember that there are certain restrictions on your angles when you use inverse trig. Okay, so what I mean by that is like when you do inverse sine, you always get an answer between negative 90 and 90. When you do inverse cosine, it's 0 to 180. When you do inverse tangent, it's negative 90 to 90, but not including the endpoints. Okay, so that might come up. That's angle restriction probably isn't as important. The Pythagorean Theorem is very important. Okay, but I'll let you know if we come across one where that restriction becomes important. All right, so let's start looking at an example. Okay, so when we're done, inside that box is going to be a formula. It might be a fraction, might not be, but it's going to be a formula with just v. It'll be like v squared plus v divided by 3. Okay, something like that. Maybe there's a square root. But the point is the sine and inverse cosine are going to be gone. All right, so directions said, start with the inner trig function, and if it's an inverse, try to rewrite it with regular trig. Okay, so for now, I'm going to forget about the sine. I'm just going to copy the middle part down. Inverse cosine of v equals. Now, anytime we use inverse trig, like if I type in this, let's do it in degrees. If I do second inverse cosine of 0.4, I get 66.4. I'll send. Okay. What is that? Like when you use inverse trig and you hit enter, you get that number. What does that number represent? Yeah, it's an angle, exactly. So anytime you use inverse trig, the answer is an angle. So when I do that out, the inside part, I'm going to get an angle. So I'm taking the sine of some angle. Well, for now, let's just call that angle theta. When you do inverse cosine of v, you're going to get an angle. I don't know what the angle is going to be. I'm just going to call it theta. Now, I said, if you can, rewrite inverse trig in terms of regular trig. So I want to cancel out inverse cosine. How can I cancel out inverse cosine? What function would cancel it? Yep. So the reciprocal of it would be, like if you had cosine, the reciprocal is secant. Not the reciprocal. Remember what it's called? Yeah.
Is it just cosine?
It's regular cosine, right? It's like square root and then inverse square root. You know, we normally call that squaring. Square, square root cancel, cosine, inverse cosine cancel. So let's take the cosine of everything that's on the left and the cosine of everything that's on the right. Now, remember the kind of problem. This is going to be in the context of a right triangle. What does that mean about that angle? We don't know what it is, but I'm telling you it's in a right triangle. Does that tell you anything about it? Yep.
It has an angle that equals 90 degrees.
Okay, so the right triangle itself has an angle that equals 90. How about theta, which is another angle in that triangle? Yep.
It has to be less than 90.
It's got to be less than 90, and that's what's going to make this problem work. Okay, there is a restriction on the angle, okay, when you take the cosine of both sides for when these two things cancel out. As long as your angle is between negative 90 and 90, they do cancel out, and I guarantee you that will happen here because it's an angle in a right triangle. So you're perfectly fine to take the cosine of each side. You don't even really need to think about it. You're allowed to do it. So now you get this. V is by itself on the left, and that's equal to cosine theta. Now we're going to make a picture out of that. They've given me an angle to label, theta. So let's put theta, doesn't matter where you put it. I'm going to put it here. And I know one thing about theta right now. There's one calculation I could do for theta, and I can tell you the answer for it. Might not be a numerical answer, but I know the answer. Yeah?
90 minus theta.
Okay, so the other angle would be 90 minus theta, but there's something I can tell you about this. Based on what I have up above. There's some function I can plug theta into, and I can tell you the answer for it. Anybody see what it is? Yeah? No? You could plug theta into some function, and the answer is already on the board. What function could you plug theta into? Yeah?
Like the beginning function, like plug it in for v.
Not plugging it in for v. It actually says it right on the board. Like, it's right there. Yep. If you take the cosine of theta, what do you get? V, right? I don't know what v is, but I know if I take the cosine of theta, I get v. Let's draw that in this diagram. What does cosine mean? How would you calculate the cosine of something in a right triangle?
Is it adjacent?
It would involve adjacent over hypotenuse. So you need to put something here and something there. So the answer is v. You can put anything you want, as long as it comes out to v. So anybody tell me the simplest way I could label the adjacent and the hypotenuse? So when I divide them, I get v. Yeah?
V and 1.
V and 1. Which side would be v?
Obviously.
Well, cosine. So what sides do cosine involve?
adjacent and
Adjacent over hypotenuse. So where would you put the v? Which one of those sides?
adjacent.
Adjacent. And then that means the hypotenuse would be 1. So now the cosine is adjacent over hypotenuse. V over 1 gives me v. So I just set up a picture for that equation. Now, what I really want, okay, the answer they want is the sine of the picture I just drew. Okay? That's what they're looking for. What's the sine of this picture? So to find sine, what side am I missing?
Opposite.
I'm missing the opposite. How can I get the opposite side? Given that I have 2 out of 3. Yeah? Pythagorean theorem. Yeah. So we're going to use the Pythagorean theorem. That will give us the third side. If you want to give it a name, you can for now. If you want to call it x, we're going to get rid of that in a second, and we're going to know what it is. So let's set up the Pythagorean theorem. X squared plus v squared equals 1 squared, which is just 1. Okay, and Gabe, what would be my first step to get x by itself?
Square root.
Minus
v squared.
Yeah, you want to minus the v squared first. So you're going to get this. And now what would you do?
Take square.
Yep, now take the square root. So x is the square root of 1 minus v squared. That's the third side. 1 minus v squared. Okay, so now we've got a diagram. We've got all the sides labeled. Now we can answer the original question. What's the sine of theta? Remember, we said inverse cosine of v equals theta. So what's the sine of that angle that we have inside? So sine is opposite over hypotenuse. So square root of 1 minus v squared over. Now in this case, it's just over 1, so you don't even really need to put it. Okay, now let's graph that. Let's graph what's on the left, what's on the right, and see if they look the same. If they look the same, then we probably did it right. If they look different, then we did it wrong. So let's do the sine of the inverse cosine of x and the square root of 1 minus x squared. If I want, I can really just go to the table and just check some values. All right, so if you plug in 0.5, notice you get the same answer in both, 0.86603, 0.86603. If I plug in 0.7, 0.71414, same answer in both. So what this means is that each formula is giving you the exact same answer. One of the formulas is all algebra, the other one has trig. Now, if I try to do this, I get a problem. Remember, the domain of inverse cosine is -1 to 1. Can't go beyond that. But what happens if you plug 2 into that square root? Why doesn't 2 work when you plug it in for v? Yeah? Then you're taking the square root of a negative number, which is imaginary. That's why 2 doesn't work there. Right? But any other number between -1 and 1 should work should be perfect, and you should get the same answer in both. Let's hit graph. Just see what it looks like. All right, let's do zoom 7. All right, so let's graph it in radians, see if that works. Zoom 7. There we go. So there's, well, it was so fast you really didn't see it. The one in blue and then the one in red was exactly the same picture. They traced right on top of each other. So that means we did it right. Okay, we're going to try another one, but that's the general idea. Any questions on that? Why do you think you might want to do that? Take a formula that has some trig in it and rewrite it as a formula without any trig. Anyone think of an advantage to that? What's easier about it?
You're not having to deal with trigonometry, so
Okay, and why might a computer like that better?
because you can actually put it into like a calculator or something.
Well, I can put what's on the left in a calculator too. But why might the calculator like the right-hand side better? Pretend you're a calculator and you get each one of those plugged in. One for y1, one for y2. What do you think the difference might be? I mean, they come out the same, but what do you think, yeah? Okay, so there's different operations you're doing, and when you do the operations on the one on the right compared to the one on the left, what might be the difference when you do them? You get the same result, but how about getting to that result? Let me graph them again. Let me see if I can, let's go like this. All right, so I have to change it, and then I think if I just change it back, it should regraph it from scratch. Watch it graph the first one. Now the second one. Anybody notice anything? Nobody? Yeah?
The second one was fast.
Yes, the second one was faster. So whenever you're making something, if you can make the computer do it faster, a different way, and get the same answer, then that's usually better. Faster is better. People wait less time. So for whatever reason, the calculator has an easier time with square roots, squaring, subtracting, and division than it does dealing with sine and inverse cosine. To the calculator, that's more complicated. So, and even for us, I think most people would think square roots and squaring is easier than dealing with this stuff on the left, right? But it is faster, at least on this calculator. Might not be faster on all, I don't know, but it is on this one. All right. So let's try another one of those. Doesn't really matter what trig function is on the outside and what's on the inside. If it's a regular trig function on the outside and inverse on the inside, you always do it the same way every time. Okay, so let's see if somebody can tell me what I should do first. What's the first thing I did in the last problem? Rob?
You divided or multiplied by the inverse, or like you separated the thing that's inside the parentheses.
It took the thing that's inside the parentheses, yep. And what did I set it equal to?
The inverse.
Theta. Yep, set it equal to theta. Because we know anytime you do inverse trig, you're going to get an angle. I don't know what angle you're going to get, so let's just call it something. Now we rewrite this. We're going to rewrite it so we can draw a picture of it. If you can jump right to the picture from this step, that's fine. You don't need to rewrite it. Okay, but some people might need to see it rewritten. So to rewrite it in terms of regular sine, how do I cancel out the inverse? Yep. Not quite. You're very close. Yeah?
V equals sine theta.
And how did you get that? I agree with you. V will equal sine theta.
Because if you multiply both of the
Yeah.
sides by the...
What am I being picky about? What you guys are kind of saying is like doing something like this. If I said solve for x and you said, oh, multiply both sides by the square root symbol, I would say, okay.
Take the inverse.
Yes.
Of the
Take the sign of both sides. Okay, when you have a function, you can't add, subtract, multiply, or divide by a word. Okay, take. Or if you can think of another word that means take, but whatever. So take the sign of what's on the left. So again, there's no multiplication happening there. And take the sign of what's on the right. There is no multiplication happening there either. Okay, just like that. That doesn't mean square root times 3. It means take the square root of 3. Same thing there. All right, so now sine and inverse sine cancel. And that's what Kaya said. So now I've got this equation. What do I want to do with that?
Draw it out.
Yep, let's draw it out. What's the first thing I want to put in that picture? Yep.
The theta.
The theta? Does it matter where I put it? Doesn't matter at all. So I just tend to put it at the bottom. If you want to put it at the top, that's fine too. All right. Now, there's one thing I know about theta from the equation up above. What's the one fact that I know about theta right now? Yeah?
The sine of it equals b.
The sine of it equals v. So we need to draw a picture that represents the sine of that equaling v. So sine, what two sides are going to be involved? Yep.
Opposite and hypotenuse.
Opposite and hypotenuse. And what's the simplest way to label those two sides? So when you divide them, you get v.
The opposite would be v, and the
Yeah.
hypotenuse would be 1.
Yeah, you pretty much use that trick every time. It's usually that one side is a letter, the other side is the number 1. I mean, you could do 2v and 2. You're going to get the same thing. And now the third step is to do the Pythagorean Theorem. Once you've done it a couple times, I think you kind of get used to what the answer is going to be. It's going to be the same answer we had last time. Right, so call this x for now. You get x squared plus v squared equals 1. And then x is the square root of 1 minus v squared. All right, so now we've drawn out our picture, labeled the missing side, and now what do they really want to know about that angle? They want to know the what of it. They want the tangent. Inverse sine v, we just drew a picture of. That was our theta. So now we want the tangent of theta. All right, tangent. Gabe, what two sides are involved with tangent?
The opposite over adjacent.
Yep, opposite over adjacent. And what's opposite here?
The V.
Yep. So opposite is v over, and what's adjacent?
Square root of 1 minus V. This
Square root of 1 minus v squared. Yep. So there's the formula. One thing about that formula that I don't like. If you were to type it in and graph it, it would look the same as what we started with, but you gotta fix something.
And it'd be v times the square root of 1 minus v squared over just 1 minus v squared.
Yep. So it's v, multiply top and bottom by the square root. That's going to move the root to the top, and it gets rid of it in the bottom. So on a test, that's probably the answer you would see, what I circled. Okay, and I'm not going to graph that one, but if you were to graph it, and you graph what we started with, they would look exactly the same. Okay, any questions on that one? All right, now, you can't just do this for anything. If you have a regular trig function on the outside and an inverse on the inside, yes, you can. But if you just made up something that wasn't this type of pattern, you're probably not going to be able to use this trick to do. All right, this is kind of another one that's the same. Does anyone need to see a third type of that one? Just set the middle equal to theta, draw your right triangle diagram, use Pythagorean Theorem, and then do whatever you need. In this case, it would be adjacent over hypotenuse. And if you get a root in the bottom, make sure you fix it. Okay, so questions on that one? All right. Okay, this one's a little different. Evaluate. That means when I'm done, I want a number, like 6. What's the answer? And they're asking us to do it without a calculator. Now, if they're asking us to do it without a calculator, then there's probably a trick to it. The angle's probably going to be an angle that's easy to work with, something like that. So whenever you do order of operations to evaluate something, where do you start? What's the very first thing you always do with order of operations? Yep. Always start with what's in the parentheses. Don't even worry what's outside the parentheses. So I'm just going to see if I can figure out the tangent of 3 pi over 4. Now, some people might be able to think about that a little easier if it was in degrees. What's 3 pi over 4 if you write that in degrees? Bless you. How about Chris? Can you tell me what that would be in degrees?
90?
90 would be pi over 2. Do you remember what pi over 4 is?
That's 45.
Yep, it's 45 and then it's tripled. So it's triple 45, which is...
I'm sorry. 135.
Yep, 135. Okay. So I'm trying to find a trig function of an angle that's a multiple of 45. That's a special right triangle. So I can do that without a calculator. So what I'm going to do is there's a couple ways. If you have the answer memorized, just go with that. If not, then you have to make your make a diagram. Here's 90. Here's 180. I'm going to put the point somewhere on the circumference of that circle. Where's 135 in relation to 90 and 180? Closer to 90? Closer to 180? Right in the middle.
So, right in the middle.
It's right in the middle. So if I put it right in the middle, okay, we went over this when we did unit circle trig. What kind of triangle did I just draw? What are the angles in it? Yep.
45, 45, 90.
Yep, it's a 45, 45, 90. The hypotenuse is 1 because it's a unit circle. That doesn't really help me. What I want to know is the coordinate of that point. And then once I have the coordinate, that's the calculation I need to do. That's how you find tangent, y over x. Or think of it as opposite over adjacent. Either way. Now, in a 45, 45, 90 triangle, how long is each side? Each leg. So these sides, they have square roots in them. Remember, yeah?
Isn't it root 2 over 2?
Yes, root 2 over 2. Very good. So this side is root 2 over 2. This side is root 2 over 2. Just remember, what about the x value? Because you're in quadrant 2. It's negative. So your coordinate, you really don't even need to write the whole coordinate. All you need to do is take the y value, divide by the x value. I'm going to put a negative there so we don't forget. So what's y divided by x in this case? Yeah, negative 1. So now, I know the answer to tangent of 3 pi over 4. The answer is negative 1. So now I've turned the original problem into that problem. Now I want the inverse sine of negative 1. Okay, so let me write that, just put that down here. Inverse sine of negative 1 equals, and what did we say when you do inverse trig? The answer that you get is always what? Yeah?
Degrees.
Or radians. Could be degrees or radians, but those are both angles. Right? The answer is always an angle. So for me, the easiest way to figure this one out is think of the graph of sine. Right? It's a wave. It looks like this. And we're looking for that where that wave hits a special value. We're looking for where it hits negative 1. You could think of it this way. If you wanted to draw this as a right triangle, you could, this is what you would do. You take the sine of each side and get negative 1 equals sine theta. But I'm not drawing it as a right triangle. I'm looking for an angle so that when I take the sine of it, I get negative 1. Well, look at the graph. This is 1. That's negative 1. I'm looking for the angle right there. So when I hit negative 1, How far through the cycle have I gone in that wave? Yeah.
One cycle.
Well, I haven't gone the whole cycle. I'm in the middle of it somewhere. This would be the whole cycle if you stop over here.
So like 3/4 of it.
I've gone 3/4 of the cycle. That's the answer to the question. What angle is 3/4 of the way through the sine cycle? Yep.
Is it 3 pi over 2?
Yeah. And what would that be in degrees? They didn't say which way to write the answers.
270.
Yep, 270. So you hit -1, 270 degrees through the cycle. If you don't remember, we can just try that and see if it works. I'm in radians, so I'll say what you said first. Sine of 3 pi over 2. If he's right, I should get -1, and I did. So that's the answer, 3 pi over 2. So 3 pi over 2, or 270 degrees. Now, a lot of special things had to happen to make this problem work. First of all, the angle on the inside had to be an angle you could do unit circle trig with in your head. That means it had to be a multiple of 30 or 45, and it was. The second thing that had to happen is once you found this answer, it had to be a nice number. The only ones that would come out nice would be like a 1, a -1, or a 0. If it came out to something besides 1, -1, or 0, it would have been very difficult to do by hand without a calculator. So that's how it'll always work out if they say without a calculator. Any question? I don't know. Okay, a little bit different because this time the inverse was on the outside and the directions were evaluate, not to come up with a formula. Right? So we're gonna do a couple that are numerical. You're gonna get an actual answer when you're done, not a formula. All right, let's look at example B, the cosine of the inverse tangent of a half, and example A, inverse sine of the tangent of 3 pi over 4. Besides the functions themselves, what's the big difference in the format of that problem? In A versus example B. Problem?
You have like an actual number, you have fractional number.
Okay, but we have an actual number here too, right? 3 times the number pi divided by 4. So they both have actual numbers, but that's something they have in common. So we're not going to have variables in this problem. But what else about the setup?
The inverse function switched places, like on the top when it was outside the parentheses and on the bottom was on the inside.
Yeah, on the top one it was outside and we just went through it. On the bottom one, it's inside. We've just done those. This problem we're going to do next is just like one of these, except it's even easier. Your sides aren't going to be labeled with letters. All your sides are going to be actual numbers. Okay? So when you're done, you'll have a number where V is, and you can actually get the answer. All right, so let's look at this one. Okay, just like we did when this argument was a letter. What's the first thing that I should do here? Yep.
You're going to start with the inside.
Okay, start with the inside. And do what?
You have to simplify it into like normal trig.
Okay, so yeah, inverse tangent of a half equals, what do I want to put on the other side for now?
Theta.
Theta. Now, if I had a calculator, if the direction said I could use a calculator, I could actually just see what the inverse tangent of theta is. Inverse tangent of a half, I mean. But I can't use the calculator, so now we're going to do it just like Chris said. And what did you say next to do with this?
Take the tangent of both sides.
Exactly. Take the tangent of both sides, which gives you this. Right. So the tangent of theta equals a half. That's all I know about theta right now. What do I want to do next? Now that I know the tangent of theta is 1/2.
The right triangle.
Yep, make a right triangle. Okay, and what do I do now?
Put your theta.
Put theta somewhere. Now you have to label two of the sides and use the Pythagorean theorem to get the third one. Which two sides can I label here?
Opposite and adjacent.
And how long is opposite?
1,
One. Adjacent?
2,
Two. So use the Pythagorean theorem to get the third side,
5.
and it's going to be the square root of 5. Now let's go back and see what they originally wanted to know. They want the cosine of that angle, the inverse tangent of a half. So I'm never even going to know what the inverse tangent of a half is. All I'm going to find is the cosine of whatever it is. Okay. So now look at your diagram. The cosine of the inverse tangent of a half. Okay. So looking at that diagram, what would be my cosine? Joe? What would be my cosine?
2 over square root of 5.
Yep. And can you fix that for me?
2 square root of 5 over 5.
Okay. So that should be the answer. Let's check and see. So if we type in the cosine of the inverse tangent of a half, and now, let's see. They didn't say whether they did degrees or radians, but I'm pretty sure they're using radians. 0.894427. Let's see what I got. 2 square root of 5 divided, oops. And then get rid of that parenthesis that I put. Divided by 5. 0.894427. So without you just setting up that diagram and going through it, you'll never get the exact answer. You could get the decimal, but you're not going to get 2 square root 5 over 5. Right? So that's why you got to go through the diagram. Okay, and on the test, I would be looking for what I circled, not 0.8944. Questions on that? Right, so kind of like the first ones, except I think it's a little easier because it's all numbers this time. This is another one just like the one we just did. Inverse is on the inside, except it's an actual number. Does anyone want me to go through another one like that? Okay. Okay. Yeah, it wouldn't be any different at all. All right, so last thing we're going to look at is what I kind of reminded you about at the beginning of class. So we're going to solve, I think there's only 2 equations we're going to look at, and then we'll be done. Remember, when you solve a trig equation, if you can find one solution, there's an infinite amount of solutions. And when we studied trig functions, how often did we say the solutions occur? They occur every what? In general. Yeah? You could have a specific problem where they occur every 90 degrees. It depends on if 90 degrees is the blank of this function. Yeah?
Every period.
Every period. So, if you can find all the answers in one period, remember you put plus 2 pi k if that was the period, or pi k, depends on what the period is. Right? But you have to put plus the period times n. So, find one solution and then put plus any integer multiple of the period. Quick review on finding period. If you're dealing with sine, cosine, secant, or cosecant, period is 2 pi over b. If you're dealing with tangent and cotangent, the formula for the period is pi over b. And if you're like, what's b? Well, b is this. B would be your horizontal, B would be the number that has to do with the horizontal stretch or compression. A, the C, and the D, doesn't matter at all. Okay, so you find one solution, and then put plus the period times n. And there's your formulas for finding the period. Again, one on the left, sine, cosine, secant, cosecant. One on the right, tangent, cotangent. If you want to check your answer on the calculator, which it's fine to check, remember you don't have a button for secant, cosecant, or cotangent. You have to flip it to type it in. It's like if you wanted to type cotangent in, you got to do 1 over tangent. Alright, so we'll start with this one. Sine of x equals 0.6. Now, usually getting the first answer is, in this kind of equation, pretty straightforward. All I have to do is get x by itself. So I just want to get rid of sine. What could I do to both sides that would get the x by itself? Chris?
Take the inverse sine.
Yep. Take the inverse sine. So plug everything on the left into inverse sine and do the same thing on the right. Now, those two things cancel out. As long as your answer is between negative 90 and 90. Well, what that means is you're going to get an answer here that's between negative 90 and 90, but it might not be the only answer. Okay, we might have to think about other quadrants to get the second answer. So x, and let's do this. Let's do it in degrees. Whether you use degrees or radians, it doesn't matter. Just make sure you keep it straight whether you're using pies or 180s. So let's do inverse sine of 0.6. So we get an answer of 36.87. And that's degrees. Now, if you want it in radians, just do the same thing again in radians. Or just multiply by pi, divide by 180, convert it yourself. All right. What quadrant is 36.87 in? Yeah. It's in the first quadrant. Well, every trig function is positive in the first quadrant. So we just found this answer. Now, go back to the original problem. Sine of x equals positive 0.6. What other quadrant am I going to find a positive answer in for sine? I got 1. Is it 2, 3, or 4? Yeah, 2. It's quadrant 2. So that means once I have my reference angle, which I already do, we just did the absolute value, well, we did the inverse sine, and we got a positive number. That's my reference angle. To get an answer in quadrant 2, take your reference angle, subtract it from 180, and that's the other answer. So let's do that. So we get x equals, take my reference angle and subtract it from 180, 36.87. So 143.13. Now, those are all of the answers in the first cycle. But the question didn't say to find all the answers just in the first cycle. It said all of them in general. So I not only want this, but I want every single time that these two answers keep repeating. So what do I have to put on the end of each? Well, what do we put in general? You don't have to give me any specific numbers, but we always put plus this times this. Plus, you have one answer, That's like in the box, and then you have to put plus, yep, period times n. Now, if you're doing it in radians, those are your formulas. 2 pi over b and pi over b. If you're doing it in degrees, it's 360 over b and 180 over b. Okay, so let's look at our function. There it is, sine x. What's b in that case? Oh, that. 1. B is 1. So when I put plus period times n, b is 1, and it's a sine function. Which one of these would I use? The one on the left or the one on the right? Once I change the pi's to 180s. Which one do we use for sine? Emily? The one on the left. So it's 360 divided by 1, which is just 360. That's just a normal sine function. You haven't stretched or compressed the period at all. So each of those answers are going to repeat every 360 degrees. Okay, let's check these two answers and make sure they're right. Well, there's a couple ways I can check them. If I don't have a graphing calculator, take the sine of your answer and see if you get 0.6. Sine of 36.87. Now, how come I didn't get exactly 0.6?
That's not exactly 30.
Right, the answer is not 36.87, exactly. Now, this is the one we should check, because this one we figured out ourselves. And the sine of 143.13 worked perfect. That is also 0.6. Right. Let's look at it this way. Sine of x and 0.6. Okay, I'm going to look for where these cross. I'm in degrees, and I'm going to graph from 0 to 720. So how many cycles am I graphing? If I go 0 to 720. 2 full cycles. So I should see 4 intersections on the screen. 2 in the first cycle, 36 and 143, and then 2 in the second cycle. Let's just speed it up. Okay, let's calculate the intersection of the first 2. Well, you know what? I'll just do the one I'm closer to. So the intersection is 143.13. That's exactly what we got. And if you did the other intersection, you get 36.87. The next time that 36.87 occurs is 1 cycle later, or earlier, but next time you usually think it later. So if you add 360 to 36.87, that's this intersection point. If you add 360 to 143, that's that intersection point. And you can keep adding 360 forever, or subtracting. But that's how you get your 2 answers. Any questions on that? Now keep in mind, if you do it in degrees, you would have had your calculator in degrees for the original answer. You would have gotten that original answer, and you wouldn't have done 180 minus your original answer. What would you have replaced the 180 with if it was in radians? How much?
Pi.
Pi, yes. You would replace 180 with pi, right? And that would give you your second answer. And then what would 360 be replaced with if that was radians? Yep. 2 pi. Yep. 2 pi and 2 pi. Right, so let's do, let's finish up with one more, and let's do this one in radians, just to practice that. You know what, if we want right away, why don't we just find the period before we do anything? So I gave you the 2 formulas, told you which one to use for tangent and cotangent. Just look at what b is in this case. We're not really doing anything tricky with b, so what's the period of cotangent x? Yeah?
180 or pi.
180 or pi. Yep, and we're going to go with radians this time. So when you get your final answers, it's plus pi n on each. All right. How do I get rid of cotangent? What do I have to do on both sides? Yep.
Take the inverse cotangent.
Yes, ideally I would try to take the inverse cotangent of what's on each side. But if you look at your calculator, what's going to be a little difficult about that?
It's not a button.
It's not a button. Yes, I agree with you. If you had a button for inverse cotangent, you could do it. You don't. So what we have to do is rewrite this. What button do we have that's related to cotangent? Somebody mentioned this earlier. It's a connection with cotangent, but it's not quite the same thing. Yeah? The reciprocal. So let's flip each side. If you flip cotangent, what do you get? Well, that is 1 over tangent. If you flip the tangent, that's the cotangent. But I'm saying, what's this? If you take the cotangent and flip it, what's 1 divided by cotangent? Chris?
That would be your inverse.
When you flip it, it doesn't change from inverse trig to regular trig. It's still going to be a regular trig function. I just want to know which one it's going to be. Yep. It's tangent. If you flip the cotangent, you get the tangent. And if you flip 2.5, you get 1 over 2.5. So what we wrote below it is exactly the same equation. But now, what's the advantage of writing it this way?
You can do inverse tangent.
We need to take the inverse tangent on both sides, and we have a button to do that. Okay? So, x is the inverse tangent of 1 over 2.5. That's the first answer. That's always the easy one to get. Well, this one was a little harder, but not too bad. So, mode, I said I'm going to do it in radians. So second, inverse tangent, 1 over 2.5. Doesn't matter if I close my parenthesis. It's about 0.38. And plus, what do I put on the end of it to show that the answer repeats every cycle? Yep. Plus pi n. So you can add 1 pi to that number, 2 pi, 3 pi, 10 pi, 20 pi. You're going to keep getting a new answer every cycle. That's one answer. All right, now, let's go back to this equation. It says tangent of x equals 1 divided by 2.5. What kind of number is 1 divided by 2.5? There's a few things you could say, but I'm looking for something specific. You divide 1 by 2.5. What kind of answer do you get? Yeah?
Positive.
You get a positive answer. Yeah, that's what I'm looking for. So it's a positive answer. 0.38. Let's look at our diagram. If you're thinking in radians, what quadrant is 0.38 in? Well, this starts at 0. Where does the quadrant end in degrees? First quadrant. 90, which is pi over 2. Well, pi divided by 2 is 1.57. Okay, so 0.38 is in quadrant 1. So we just got an answer there. We're looking for where the tangent is positive. Where else does that happen? Yeah?
Third quadrant.
Third quadrant. That's the answer we need to figure out. So we've got our reference angle, 0.38. Your reference angle is just the answer in the first quadrant. Now, If you want an answer in the third quadrant, what's the formula? It involves your reference angle and something else, and then you do some arithmetic. Yep.
180 plus.
180 plus the reference angle. What about if we're in degrees? What if we're in radians? Sorry.
Pi.
Pi. Pi plus your reference angle. 3.52. Plus pi n. Okay. I'll check the second one just to make sure it works, but I'm pretty sure we're good. When you check it, it doesn't matter if you type in the original problem or the tangent problem. They're the same thing. I'll type in the original. So 1 over tan, don't worry about the parentheses, and 2.5. Now before I hit graph, what do I have to check? Because I changed my mode. Because if I hit graph right now, you're not going to like what you see there. So you could probably get that and be like, well, okay, I did something wrong. What's wrong with that? It's a lot of intersections. It's going to take me a while.
Well, you said it's like a long cycle.
Yeah, that's way too much. The cycle here is 0 to 3.14. I'm going all the way to 720. That's a couple cycles. So if we just set it from 0 to, let's go 0 to like 2 pi, you'll be able to see both of those answers, I hope. I want you to see if you recognize something. Second, calc, intersect. Let me do the second one. So in the second one, I get an answer of 3.52. And the first one would be 0.38. And technically, there's nothing wrong with writing what I did right there. But does anybody notice anything about those two things that I circled? All we did is we just kind of followed all the steps. We got the answers, but let's look at this last one. If I start listing the answers here, right, let's just take 36.87 and let's list the next positive answer. So plus 360. I get 396.87. The next answer after that is 756.87. Okay, and I'll list one more. The next answer after that would be 1,116.87. Those are the kind of answers I get from the first formula. Now, let's look at the ones from the second formula. 143.13 plus 360. So your next answer is 503.13. Okay, the one after that, 863.13. And I'll do one more. 1,223.13. Is there any overlap in the answers you get from the first formula and the second formula? Not me? What do you think?
What? Sorry.
Is there any overlap there?
I don't see any.
No. Will there ever be any overlap? Because I only listed the first 3. What if I went out to the first 3,000? Do you think there'd ever be overlap? What? No. They would never overlap. You're starting at 2 different starting points and adding 360, so you're never going to have the same answer in both lists. Okay. Let's look at this one. Let's write out some of the answers here. Okay, it's 3.52, plus you keep adding pi. Okay, just to be simple, I'm just going to do 2 digits. So 6.66. Next one, 9.80. And these are rounded. And 12.94. Okay, let's list out the answers in the first one. 0.38 plus 3.14 gives me 3.52. Okay, let's do the next one. 6.66. And the next one. Oh, the next one's just going to be 9.80. Is there any overlap in the answers between those lists? They're the same numbers. You just said, it's like saying starting on this tile and then moving left 3 units. Or starting on this tile and moving left 4 units. You just said 2 different starting points, but you can get to the exact same spot. Doesn't matter because the starting points are exactly 1 cycle apart. That's what makes this one a little different. So technically, all you have to say is either 1 or 2. You don't have to say both. They're the same thing. In the previous problem, they are not the same thing because these are not 1 cycle apart. This is like starting on one tile, and then the next one is starting like in between tiles. So they're different answers. Okay. If you didn't notice that, it's not a huge deal, but you really should just write one or the other. And that's how you can check. Just see if this number is exactly 1 cycle away from the other number. Okay. Any questions on that? All right, so we went over getting rid of the algebra, okay, from a trig function, okay, or converting it all to algebra, sorry. And then the second thing we looked at is evaluating without a calculator, but it has to work out nice to do it. And then the third thing, evaluating with a calculator and writing your answers just like that, okay, either degrees or radians. Okay, there's not really a lot of different concepts we went over, so the homework, just those questions. 37, 38, 41, 42, and 44 to 53. Okay, we'll take a look at that tomorrow. And then we got a little bit more to do with trig equations. And then I think on Wednesday we're going to look at trig identities. And Thursday should be review.